Welcome back, I'm Pi, and today we're going to be taking a look at problem number 23 from the 2014 AMC 10A. A rectangular piece of paper whose length is root 3 times the width, this is y root 3, this is y, has area A. The paper is divided into 3 equal sections along opposite sides, and then a dotted line is drawn from the first divider to the second on the opposite side as shown. The paper is then folded flat along this dotted line to create a new shape with area B. What is the ratio B to A? So, because it seems straightforward enough to find the area of a rectangle, I want to take a look at the area B, which is the area that is formed when this trapezoidal shape over here is folded over. So it seems easier actually to take a look at this as a triangle and a rectangle, so that's how I'm going to start off. But I also want to do something with my area with my side lengths before I get started, and that's taking a look and saying, if this is y root 3, this whole thing, then each of these sections is going to be y root 3 divided by 3, and I don't want to have to deal with these fractions. So instead, what I'm going to do is say y equals 3x. And this way, I can say that's x plus x plus x. And so I really just can rewrite my side length as x root 3 plus x root 3 plus x root 3. And that makes working with it a lot easier because I'm not dealing with any of those ugly fractions. So this just gives me x times 3, which is 3x on this side. So taking a look at this triangle first, I see that this side length is x root 3 and this side length is 3x. And what that shows me is that this is a special type of triangle because I see that x root 3 times root 3 is 3x. And that means this longer side over here is square root 3 times the shorter side, which shows me this is a 30, 60, 90 triangle. It's going to be our 30-degree angle, and this is going to be our 60-degree angle, because if you recall, the smaller angle is opposite the shorter side, and the larger angle is opposite the longer side. So now I know, just so I can jot it down, this hypotenuse is going to be 2x root 3. And now I want to see how this is going to fold over. So when I fold this piece over, I'm going to say, I can almost imagine picking up a piece of paper, and it's going to make this angle of 60 degrees where I'm reflecting it. So here's our 60-degree angle in between. And now I don't know where this is going to go. Is it going to go here? Is it going to end up matching? Because it'd be super convenient if it ends up just touching the vertex. And how I'm going to figure that out is taking a look at this angle. Well, if this is 60 and that's 60, I know these three angles are supplementary, so this also has to be 60. Considering this is a 90-degree angle, I have another 30-degree angle, and bam, this 30, 60, 90 triangle, which is going to be similar because it folds over right about here, is going to be hitting the vertex exactly, which is convenient for me. Let me clear up this diagram just a little bit. And remember, we have this 30, 60, 90 triangle. We have this 60-degree angle that it reflects over, touches the vertex. And so we know that it's going to fold over here. Next, I want to take a look at how the rectangle is going to fold, because is that going to go to the vertex also? I don't know yet. Well, I do already know the way this triangular slice flips over. So if I turn this into a triangle over here, if I just break that last rectangle up, then I can see that this is going to be, this triangle over here, going to be identical to this triangle, because if this is 60 degrees, this is 30, then this will be 60, and this will be 60, so I have an equilateral triangle. And these guys share an angle, and I know this is just, this triangle is just that triangle flipped over. So I know if I flipped it, this triangle, triangle A, would flip right into triangle B. Now I'm going to take a look at this last part. I see that this is going to be x root 3 and this is going to be 3x. So again, we have a 30, 60, 90 degree triangle. But when I fold it over, it's not going to go all the way across. In fact, I'm going to think about reflecting it over this dotted line over here to sketch it out. And when I do that, I end up sort of making this, it's kind of like that, and it's going to go over here. So my triangle, if you notice, it kind of flips over by reflecting over that line. And so it's going to stick out a little bit at the edge. So let me trace my new shape. I have this side, this equilateral triangle in the middle, which was from the other equilateral triangle being flipped over. And then this little piece, which comes from that edge over there. And then this piece, which has always been there. So now there's two ways I can go about this. I can either calculate this entire area B by taking a look at this shape, or I can use a nifty little trick. So I'm going to break this up into two 30, 60, 90 triangles because that's how we did reflect it. And I'm going to say 1, 2, 3, 4. There's 4 30, 60, 90 triangles. And I'm doing this because I only want to find the ratio. I don't really care about the area of B. Because when I go back and look at my initial rectangle, I see that there's going to be 1, 2, 3, 4, 5, 6 30, 60, 90 triangles. And so the ratio B to A is going to be 4 to 6, or 2 to 3. And sure enough, 2/3 is option C right over there. Thank you so much for watching this one. This definitely required some, you needed to be able to see these 30, 60, 90 triangles, and it was much easier to approach this by components. There are a couple of other solutions. You can likely approach the divisions into triangles in a few different ways, but I just found it convenient to flip one part over at a time. Thank you all so much for watching, and good luck on the upcoming AMC.